Good morning, all. So, as you can guess from my accent, I'm not a typical Alaskan. And I really started studying volcanoes and volcanic research during my PhD time. And then in December 2005, I moved to Alaska. And what you'll be seeing in the first half of our part of the workshop is a sort of overview of volcanoes, some example volcanoes that exist across the North Pacific. Then Kathy will give a little bit about how ash moves, and then I'll finally talk about this puff model that we use in Alaska as part of the Alaska Volcano Observatory. And the reason why we want to know where ash is, as Kathy said, is for the aviation industry. We all know about the 6 days of air closure that happened in Europe last year, which in the end is about $4.5 billion worth of loss to the European economy. So the knowledge of air traffic and the knowledge of where ash will be is important, not just for the aviation, but for the whole globe. So in Alaska, the sort of volcanoes are something that have been around for hundreds of thousands of years and will be around for hundreds of thousands of years. In terms of science, volcanoes have been there longer than the scientists have been analyzing them. In Alaska, we have more volcanoes than the rest of the US put together. We have more earthquakes, more coastline. Right now, we have 50 potentially active volcanoes in the state of Alaska. And in the local history, there is one volcano in particular in the mid of the Aleutians. It's called Chitinadak Island, and the Aleutian history is that the first man and woman were set free from this island. And this history comes round to that the women and man were thrown from this island into the sea. And their history describes that this was like a volcanic event. This volcano is the most active volcano in Alaska, and it's actually called Cleveland Volcano. And right now, this is within Alaska at elevated alert. We have 4 different alert levels, and this is the only one right now that's at an elevated alert level. And has been showing, even as of Monday night, was showing activity. The evening report showed ground surface activity at this volcano. And this is also the only volcano in Alaska where there's been a loss of life on the ground. During the Second World War, there was a pilot that thought he'd go up and have a look at the volcano and went up to the top and never came back. So it's the only loss of life from an Alaskan volcano on the ground surface. So active volcanoes occur all the time. Since I've been in Alaska in 6 years, we've had 5 major eruptions, and we have volcanic activity in the North Pacific every 1 to 1.5 months for the last 40 years. So the activity that you hear of in Europe that happens every 10 years happens in the North Pacific, and especially in Alaska, 5 or 6 times a year. So it's a common experience for us in Alaska. First volcano observatory really globally was the Vesuvius Volcano Observatory near Naples in Italy, which was set up to monitor the activity coming from Mount Vesuvius. And over the years, this observatory has developed with time and is now, as we can see, if I go back one, as we can see from the bottom right-hand corner, one of the most advanced volcano observatories in the world. We have next year, in 2012, the 100-year anniversary of the Hawaiian Volcano Observatory in the United States. The Alaska Volcano Observatory, which myself and Torga are part of, is about 24 years old. It started in 1988. But the Vesuvius Volcano Observatory has been around since about the 1840s, 1850s. As a volcano observatory. So in Alaska, as I say, been around 24 years. and was mainly set up after the 1986 eruption of Mount Augustine. And its first real big event that it was involved with was the 1990 eruption of Mount Redoubt volcano. And that's why you see the eruption cloud on the logo, and it's also on my t-shirt, is actually from that eruption. And we'll later on show you an audio recording of when an aircraft went through an ash cloud from this eruption. So AVO itself was the first real observatory around the world to use what we call satellite data. Alaska is very remote. Volcanoes can be maybe 1,000 kilometers from the nearest population center or from the nearest volcano part of the observatory. So we have to use satellite imagery, and as part of one of the breakout sessions, you'll work with Torg and go through how we use satellite data to detect where an ash cloud is. So you can see AVO is three groups, made up of three groups. USGS, so the federal side of geoscience across the US, then the university that myself and Torg are in, and then a third acronym is the State Geological Survey. And we make use of all three of those during a volcanic event. Obviously, the federal location is the one that produces all the information. The state can liaise with the governor and the local state organizations, and the university provides a lot of the manpower. About half of the manpower in the observatory comes through the university, because as you know, students can help you with a lot of your work. So we actually get graduate students like Torg that can pull 24-hour shifts and monitor data for us when all of the faculty and all of the other employees are fast asleep. So Torg's smiling at the back as I say this. So here's two examples, two photographs. The large one is the Redoubt eruption, which is on our logo, and the right-hand one is Mount Augustine, taken from a camera on the island from January, February 2006. And then in the bottom image, you see our monitoring room in Fairbanks, where we have about 10 computer screens now that are continuously displaying data that is then used both in outreach and in real science on a day-to-day basis. So here's a schematic, let's say, of a slice through a volcano. The volcano itself generally will show precursory, what we call precursory, so pre-eruptive activity. And what you will get is you'll get magma rising within the chamber or within the conduit, which will start to increase seismicity. So you think earthquakes. So we'll call those volcanic earthquakes rather than tectonic earthquakes, which you get mainly in this region, the Californian region. And then just before there's an event, you'll then get material on the ground surface. You might have a small flow, and then this will lead to an explosive eruption, when you'll then have an eruption cloud, an eruption column, and everything that can then occur on the surface can and generally does occur. Ashfall, lava flows, what we call pyroclastic flows, block and ash, and most people in this northwest region of the US are obviously used to the visual images of the Mount St. Helens 1980 eruption, which was a side explosion which blew away about a third to half of the volcano. And normally that's not a general case for most volcanic eruptions. Most volcanic eruptions will produce an eruption column, an eruption cloud. This side-on explosion was a fairly uncommon event, and that's why it was such a large eruption. So here's 4 examples across the North Pacific of volcanic or volcanoes. So a shield where rather than having a cone-style dome-style event in the bottom right, you actually have a growing material that eventually just produces what you would think of as putting a shield on the ground surface. It's a lot slower. Stratovolcano, this is what we all think of as the pointy volcanoes, typical volcano shape. When someone says draw a volcano, they'll draw a triangle and stick it on the ground. And that's what the typical shape is. We then have calderas. These are generally formed from large explosive events. Okmok, which is out in the Aleutians, this caldera was formed about 50,000 years ago, and actually has now individual cones inside the caldera. And we had the most recent eruption from this one in 2008. And then Bezimiany volcano, which is in Russia, has a dome at the surface. And this is an example similar to St. Helens, which has that dome growing now within the crater that was left from the May 1980 events. So 3 examples of what you might expect to see when you see a volcano. But volcanic events are not a localized issue. We all know from Eyjafjallajökull, and try saying that quickly 3 times, in Iceland, that ash clouds can travel hundreds of thousands of kilometers. Here's an example from Alaska just nearly 20 years ago now, where using satellite data, an ash cloud was tracked from Alaska to Greenland. This even caused airport closures in Cleveland, Ohio, which was always a strange one to say because we have a volcano called Cleveland. And when we were informing people that Cleveland was closing, they were like, "Do you mean the volcano or the city?" So you always have to give more information than just saying the locations. But Cleveland, Ohio, there was, as you can see, this is satellite data. The dark area generally means more ash. And this volcano produced airborne ash over the Great Lakes, which was really a major unheard of event from an Alaskan volcano. What I'm going to show you now is some video examples, both video and audio files of an eruption. This is Okmok from July of 2008. And these are individual earthquakes that have been raised up to our ear level. Normally you can't hear these. These are earthquakes in the ground. And that's the eruption. So those were small earthquakes occurring beforehand, followed by what sounds like a jet engine going past. This is from a site about, you can also hear that cutting out of the signal. This is coming over radio, and it's one location, repeater station, volcanic ash cloud in the middle, blocks the signal, so you can't actually get data through. So this was July of 2008. And we were like, okay, great, we've had our volcanic event for the year. Then we had this one. This is Kasatochi volcano, which at the time a lot of people didn't think could produce a volcanic event. And then we had this. That was from 40 kilometers from the volcano. So I'll stop that. So that was 40 kilometers from the volcano. And I don't have a laser pointer, but it was from the station on this island, the large one, to the... So for those that are on the other side, it's the large disc-shaped island to the east, over here. That was the station that was being used to record that information. And this produced an ash cloud that traveled from the Aleutian Islands to Seattle, which is 2,500 kilometers. And just quickly, before I pass over to Kathy to go through some hands-on audio and video files that can be used in the classroom. In 1989, there was a KLM encounter, a Dutch jet with an ash cloud from Mount Redoubt. And what you're going to see on the screen is the text from the voice box recording from the first officer and the aircraft person on the ground, and also the audio file.
Heavy is reaching level 250, heading 146. Okay, do you have a sight on the ash plume at this time? Yeah, it's just cloudy. It could be ash. It's just a little browner than the normal cloud, but we don't know. We have to go left now. It's smoky in the cockpit at the moment, sir. Kilo 867 Heavy, roger to left, at your discretion. Yeah, we fly level 390 in a black cloud, and the heavy is 130. Kilo 867, we have a fallout oasis, and
So this was at the time, as you can see, they knew there was an ash cloud there. There'd been a report. The observatory had been around for about a year or so, and they knew there was an ash cloud, but as you said, it looked a bit browner than a normal weather cloud that they're used to. And this was in 1989, and the policy at the time was to, as you deal with most weather, is you try and get above or below it. So it was to rev the engines, climb to 39,000 feet, and then try and get over the ash cloud. However, they caught the very edge of the cloud, they revved their engines, put more material through the engines, the material got melted, went through, cooled, clogged the engines, stopped the air intake. They lost all 4 engines. At the time, they didn't think that they could lose 4 engines from ash. They went from 39,000 feet in the air to 3,000 feet above the mountains that you see here in this view. The reason we use this audio is because they survived. We wouldn't use it otherwise. And there has been no loss of life from aircraft and ash clouds. They got 2 engines restarted and landed at Anchorage Airport. When they landed, they stopped on the runway. The air traffic control said, "Could you please move off the runway?" They couldn't, because once they got the wheels in place, the wheels were locked and they couldn't actually turn the aircraft. They had to land by using their side part of their windshield. The front windshield had been pummeled by ash. And at the time, it was the actual whole eruption itself was about $100 million worth of to the loss to the industry and the local community. About 1/10 of that was just cleaning this aircraft, putting in new engines, putting on a new windshield. So since this has happened, for those that will be flying home, do not worry. There is now a massive system put in place by the International Civil Aviation Organization. There are 9 advisory centers around the world that produce 24-hour information to the aviation community. And there have been 2 major encounters with ash clouds, and the last one was in 1989. So the number of events has diminished dramatically. And 24 hours a day, the aviation community, and they even train their pilots of how to deal with ash clouds, what to do. And the policy now is to turn around at a safe banking turn, because the main thing to know is that the ash cloud was not where you were 5 minutes ago. So go back to where you came from.
Okay, isn't he wonderful? He'll come back in just a minute. I wanted to talk to you a little bit about some flash animations we have online that you can use in your classroom. A lot of students are used to that schematic of how a volcano is built. Basically, I am going to start this, and it is going to grow a warm lava. Let me see if I can move it down just a little bit more. Anyway, you'll see it grow in layers, and I'll come back to it in just a minute. But it shows that you have an eruption, and you can go right to the website. I've designed this so that it is easily downloadable for a classroom. It can... Anyway, to me, a lot of students, we have worked in Alaska for many years. We've worked with about 500 teachers and more than 6,000 students, and they've all field tested these. They've come up with what they feel is most important for students to be able to understand. And this is just one animation that we have here. We also have an animation for the Shield volcano. So I'm going to go through another one. I found that this was very helpful when talking about tephra. Tephra is the solid material that has been shot into the air or underwater by an explosive volcano. This is the one that students are most familiar with, and that's ash. Again, we're coming a little bit farther down, and I'm sorry about that, but ash is the smallest tephra, and ash is the one that is so light that it can be carried in the wind around the world. On the flash animation, I also like to show students an image of what ash looks like once it's been in rock. So you go to cinder, which is the next one. It's the medium-sized tephra, and it's heavier than ash and usually falls a short distance from the volcano event. They do have things called cinder cones, and here's a cinder cone, Mauna Kea, on the Hawaiian island, the big island of Hawaii. Then I like these. These are bombs. Bombs are thrown into the air during an eruption as hot liquid. They cool into solid forms while flying through the air. If you could see the whole image, you would see them falling down on the ground near the volcano. But again, here are some solidified bombs. You can see they're about the size of a nickel. And contrasting that with blocks, which are the largest solid tephra, and obviously they are falling very close to the volcano. Well, you can't see the whole thing, but you will be able to once you get to your station. There's an example of it. That's a 14-ton block, and they're large, jagged blocks, and they usually fall very close to the volcano. In any case, I find that that's very helpful when talking to students about ash and material ejected from the volcanoes. These are computer predictions. What we're going to be hearing about in just a minute is the PUF model. And computer models help scientists predict where ash plumes will travel. These, again, are an animation that Peter will talk about in a minute. But you can see that they often are color-coded to indicate both heat and, well, not necessarily heat, but altitude. Here's one from Alaska. And you can see the stars sometimes indicate where there are communities living and where they expect the ash to be going. So when you get to your tables, this is all on the Alaska Science Education Network, and I have them there for you. And when you come back to the table, I will give you the URL for that. Now, what I'd like to do is I just wanted to, in the middle of the science, in the middle of our presentation here, the science presentation, I wanted to give you some tools that you can use in your classroom that are already made so that you can describe these volcanic processes to your students and have an animation going. So I will give you that. We've got maybe 6,000 more images like that. So I just picked the ones that went with the lecture. So Peter, would you mind continuing on with the rest of your presentation about PUF? Okay. Back across the Atlantic to the British. So PUF is used by a volcano observatory. There are around the world about 70 volcano observatories. We have a world organization, which I'm one of the chairs of. And we use PUF because normally when you hear an observation, someone says there's an ash cloud in the air and it's at this location. Well, that's great to know right now, but for hazard and for risk, you want to know where it's going to be in 6, 12, 24 hours because you need to plan. As a scientist and as an aviation manufacturer, they need to know if they're flying from, for example, Singapore to Sydney tomorrow, they need to know if a volcano erupts, which is my safe route to plan for. So when you fly, they do a 24-hour in advance planning. You speak to a planner and they'll say, okay, and this flight's going off tomorrow at 8 a.m. Where can I fly to? What are my safe routes? What are my safe airports? They have to have 2 airports that are available to them as backups to their original airport that you're going to land at. They always have to have those 2. So one of the many volcanic ash models that exist around the world is called PUF. And what PUF tries to represent is any ash cloud erupting from a volcano. These are an example images of 2 types of volcanic clouds or volcanic plumes. The strong one is your typical image that you think of for a volcanic plume, where you have a very strong sized eruption. You have a local weather system, wind direction, wind speed, and the amount of energy from the event is bigger, stronger than the crosswind. So you have a nice eruption column, and then the wind direction will move the cloud. On the right-hand side, you have what we call a weak cloud, where the volcano will erupt, but there's a very strong crosswind. So, for example, if this happened in Los Angeles last week when there were 100-mile-an-hour winds taking down trees, then it's unlikely that you would get the strong plume because the crosswinds in the atmosphere are so strong that it can't actually form what you think of as a typical column. So in terms of what we have to do for volcanic ash clouds is you also have to be
a meteorologist as well as being a volcanologist, because you've got to understand the atmospherics as well as the volcano itself. So I'm actually trained in geophysics, but I'm also have a master's in atmospheric science, which actually helps a lot in the observatory to have both backgrounds in both areas. And as I say, why do we need to model it? Why do we need to use computer models? Why can't we use real observations? Well, real observations aren't available 12 hours into the future. If they were, we'd all be out of a job and they'd be able to tell us what we're going to do tomorrow with 100% reliability. So we need to know where the ash is going to go. The other one is what we call in science or in operations, situational awareness. A volcano erupts frequently, but volcanoes have activity before an eruption. So what we like to do is we like to say, okay, if this volcano erupted, where would it go? Hasn't yet erupted, but it could. So planners can be involved, can use this information for hazard awareness. If a volcano erupts, which communities are going to be hit in 12 hours' time? What do we need to evacuate? Where do we need to move people? What areas are safe to be used for hospitals? Which airports need to be closed? When we had the 2009 eruption of Mount Redoubt, they moved all of the aircraft from Elmendorf Air Force Base, which cost the military $1 million, because the volcano was predicted to erupt, and the next 3 days it was going to impact the airport. So they moved all of their aircraft from Alaska to Lower 48 to get all the troops home from out in Afghanistan. As a result, when they were bringing the troops back, if they'd left them in Anchorage, they couldn't have got out because the aircraft would have been grounded because the volcano erupted. But they had to have that prediction 2 or 3 days in advance to know if they were going to be impacted. So they moved the aircraft, and it was a good choice to do that. So the PUF model. You can see here that there is an internet address at the top. You will all get a 2-page handout with this on the back when you come round the tables at the back. This is web-based. You can use and view this anywhere in the world. It can be used in classrooms. We use it in graduate classes. We use it in graduate projects. And with myself at the back, we'll go through the use of this website, both for events occurring right now, predictions for right now, and then we'll actually go in and run the model through the web. So you can see here that through this interface, we have about 40 volcanoes globally where we run a prediction. These run 24 hours a day and are displayed through the web. All of these volcanoes are not active right now, in case you were wondering. These are volcanoes that have had activity in the last 2 years, and therefore really are watched by the local observatories for any potential new activity. So not only is it an area in Alaska that we do this for, but we also do this through contacts to other observatories in Indonesia, Italy, Iceland, Chile, Argentina. This is what we call WebPuff. Again, this is on the handout that you'll get when you come around the modules, so there's no need to write down the web address quickly. You'll get a copy of this to take home with you. But you can see here, this is a little bit more complicated. The main web page is just some clicks to take you through to the most recent prediction. This one, you can run your own prediction. We actually had students, both high school and middle school students in Alaska, use this for class projects. We even had a high school student, as part of a summer camp, use this to make their presentation to the rest of the students. They actually went through and described the model, and he'd never seen it before until 10 days earlier, and then stood up in front of 140 students and explained the model. Nearly as good as I could, which was... and he came from Boston and had never heard about volcanic events and never even seen the model. Spent 10 days working with it and then stood up in front of all his peers and explained the model, which I thought was impressive. So you can run it for any volcano in the world. You can run it for any date going back to 1970. We all hear about the ability to forecast weather. Well, this is using the same wind data that they use for weather forecasting, but we can now use it for volcanic ash modeling. So it's both real-time as well as past events. I have an example here for Iceland showing that there was an ash cloud that did go over Europe, so they did make the right decision. even though, in my personal opinion, it didn't need to be closed for 6 days. The only reason I know that is because when Iceland erupted, I was in Europe, and I was stuck for 6 days, and was interviewed by a lot of people for my personal opinion on what I thought had been done. And I had to give the answer of, yes, they've done everything correctly. However, in the back of my mind, I felt that it probably shouldn't have been closed. It was closed from Thursday afternoon till Tuesday morning, which pretty much meant that there was no aircraft flying in Europe for 6 days, hence why there was a huge loss of money. So here's an example. This is Cleveland Volcano. You can go through the website. All of these are clickable links. You can choose the volcano. Here's Cleveland, and then it gives you a list of all of the different start heights. You then choose your height of interest. You go through, and then it's an animated file that then animates on the computer screen. The web page link never changes. However, the most recent prediction will appear on there. So if I go there tomorrow, it won't be today's prediction, it'll be tomorrow's prediction, even though the website doesn't change, which is really important for situational awareness. Is you want one location to go, and you know that every time you look at that location, it's the most recent. As you saw, there's lots and lots of volcanoes. I made this, one other area that I have to work on is computer programming. So I made this web page here that rather than having to go through the whole website and click and point, is that this is actually drop-down menus. Left-hand side is the volcano. You choose the volcano. You say latest, which will be 3 or 6 hours, at least 3 or 6 hours ago minimum, and then the previous, which is the one before that. So we store at least 2 runs available. We don't have more than that just because of computing power and server issues. You say, what would I like to be? On the right-hand side, this will be an animation. On the left-hand side, this will be a still image. You choose your start height, and then you would click choose. If Kathy can just go forward on the tab, then what happens is that through this interface, the left-hand side is your still image to tell you where the cloud would be 1 hour after the start. The right-hand side is the animation of the 24 hours. And you can then choose the next volcano and look at that. Another one we do is we use Google Earth. It's a great visualization tool, and it allows us to display our data without having to worry about missing any important population centers, communities, towns, and villages. And this is what you're seeing as an example from a Russian volcano. And you, using a tool in Google Earth, you can run animations and display the ash cloud location. Yes, and on the bottom you can see that what you're seeing is ash at multiple altitudes. So this is above sea level. And you can see that although it looks like one plume, it's actually at multiple elevations in the atmosphere. And here we have an example for those that were around when Mount St. Helens went off in May 1980. This is a visualization in Google Earth of that eruption. And what you actually can see is not only can we do them as 2-dimensional images, we can actually do them as 3-dimensional ash clouds in Google Earth. So this is a view, if Kathy could go back one more, sorry. This is the straight down view on the left-hand side, and you can see all of the towns and airports that were closed. And then on the right-hand one is a view as if you were flying into Seattle Airport when the eruption went off. And this is up to 30 kilometers altitude. Here is a map from the number of events in the North Pacific for 40 years. This is their location 12 hours after each event and then made into one map. So you can see that there's no area really that's getting away with ash clouds in the North Pacific. We have events all the way across the region. And then this is an animation that's also available through the website. If you go to the PUF site, and I'll show you everybody when you come through my station, the PUF site, where this is actually the animation of those ash clouds that made that composite. This goes from 1973 to now. The white lines in the background are the major air routes, and when there's an ash cloud encounter, the animation stops for a second and shows the location of that ash cloud. These files are about 200 megabytes, so they're fairly large, so you probably need a good internet connection to download some of them. But in terms of the number of events, I've gone back in the time series, and we've had in 40 years 383 separate ash clouds in the air, which is 40 years times 12 is 480. What's that? 480 months. So not far off, one a month for 40 years. So it's a common appearance and common activity in the Alaska region. So that's the overview of the science and some of the audio files that Kathy went through. So I'm just going to hand Kathy the microphone before we start the process of breaking off into groups and going through the 3 stations. So thank you for listening to me. And now we're going to go through some hands-on activities where you'll actually get to go through 3 exercises and 3 lessons that we've put together.
Here you can see they have a testable question, and this aligns with that flash image I showed you about tephra. Because one of the things that the students were most confused about when we were talking, that's a different pressure, that's a different force, that's probably going to be on the spoon, you know, a different amount of catapult. What I've done with, if we have, this says to do 10, but
Color-coded by altitude, and the page will automatically refresh as well. So you don't even have to worry about doing F5 on your PC. Most volcano observatories have their own website. ABO has its own. It's ABO.Alaska, but it's maintained in the university. So it's very hard to get to. But if I go to so I go to another volcano, let's choose one somewhere up in the eruption chain.
So do you make new meteorological models based on the activity of volcanoes? If a new one pops up somewhere, you're going to create new models for it?
Yeah, so the moves
How far is this? That's 3 feet. This is in 3 feet. Okay. Oh.
you know, tape measure. But I thought you guys might want this yardstick better.
It's more like what we'd have in the classroom anyway. That's what I thought.
And also I want.
I'm not doing it in a way that we're getting the results we wanted.
Yes, that's one of ours.
So I'm getting the same distance, but maybe the averages will drop.
Oh, wow. That one had a negative bounce. Interesting.
Kind of get your rotation speed, how much edge is in different locations. Which can be similar to the colors, but can be also different.
What we have is
Great.
And number 1, how many minutes?